The next speaker online from China again, from the same school of our first speaker, Dr. Fang from Zhejiang University. Dr. Feng, postdoctoral fellowship, associate professor and associate researcher. He obtained his PhD from Zhejiang University in
everyone, this is
2015.
Feng from
The main research interests are polymer separation membrane and antibacterial and antiviral materials. Each undertake 4 projects, including National Natural Science Foundation, China, postdoctoral fund project, in enterprise project again. Also, Professor Fang, he is ready.
University, China. I'm glad to attend the 3rd International Conference for Membrane Technology and its application.
Dr. Fang will speak today about
pity
the
that I cannot go
possibility
to
charged
Hilo.
nanofiltration membrane for ion separation. Okay.
To meet my friends.
Please, Dr. Fang, you hear me?
I will introduce my recent work
Is it
on
recorded?
positively
Okay.
charged
Here,
nanofiltration
program will
membrane
be-
for ion separation.
Recorded.
Here are the outline of this talk. Here we will introduce 3 types of the prepared strategy for the positively charged membranes. What is the membrane? I think everyone here knows where I want to introduce much. We direct go to NF membrane. NF membrane have the moderate separation accuracy and moderate formation compared with UF and RO membranes. Due to its specific pore size, NF membrane is usually applied for the separation or removal of the multivalent ions and small molecular weights. Here are the composition of the typical NF membrane, including polyester non-woven supports, polysulfone UF substrate, and a cross-linked polyamide layer with thickness between 10 to 200 nanometer. Due to the hydrolysis of acid chlorine groups, the carbon oxide acid groups were formed with the pK around 4. Therefore, the membrane carries the negative charge under the neutral separation environment. Here are the main separation mechanism. For the NF process, one is the size sieving effect and the other one is donor repulsion effect. For EF and MF membrane, the size sieving is dominant. However, the dominant repulsion plays more and more important role when the pore size becomes narrow. Since the pore size of the NF membrane is in the range of the hydration layer of ions, according to typical NF membrane, facilitates the calcium to pass through, while it shows the high reaction towards ions. In some situations, the typical NF membrane cannot meet the efficiency for the calcium separations. Therefore, NF membrane carries positive charge should be developed. What is the positive charged NF membrane? It means there's some sufficient positive segment covers the separation PA layer, in which the self-charge becomes positive at the aqueous solutions. The positive segment include quaternary ammonia groups, PI chitosan. With the donor exclusion effect, the positive charge surface shows the high rejection towards calciums. Therefore, it's easy to solve the following problem: the system with the similar size but different charge or density. One example for monomer valent and divalent ion separation. The ions show the similar hydration radius, while the different charge density would generate different repulsion force towards ions. Accordingly, the positive charged NF membrane show great application prospects in water softening for drinking water production, listen extraction from the salt lake, heavy metal removal for water reclamation, and biomolecular refinement. According to the Web of Science data, the publication related with the positive charged membrane increased sharply, especially after 2006. More researchers began to focus on this membrane. In following 3 slides, I will briefly introduce the preparation means of the positive charge NF membrane. As mentioned above, the main positive charge segment are quaternary ammonium groups, PI, chitosan. Therefore, also all the methods introduce such segment onto the separation layer. First one is the surface coating. For example, PDM and PI were deposited on the surface under the catalysis of the copper sulfonate and hydrogen peroxide. Self-oxidation of the PDA cross-linking between the PI and PDA, chitylation of the copper ions with PI-PDA complex simultaneously happen, leading to the positive charge on the surface. Second one is the interfacial polymerization or reaction. In this example, calcinic kerf was formed on the support layer directed to form a separation layer. A third one is the layer by layer assemble method. Here is the authors introduce a nickel hydrogen hydroxide to enable the surface with positive charge. The PA and the PI were coated onto the substrate in turn. The final surface charge of the membrane is determined by the final coating layer. Generally, the final PI layer enters the membrane with a positive charge. The fourth one is the phase separation method. Here the example, PI was firstly modified with decarbonate to obtain the nanocapsule. During the phase separation process, carbon dioxide is produced from the PI at a bulk, and the PI was formed again during the phase for membrane formation process. The membrane formation and the institute chemical modification is achieved at the same time. The membrane was endowed with a positive charge due to the reformed PI. Well, the final method is surface grafting. Due to the reactivity of the acyl chloride group after interfacial polymerization, several work focus on the surface grafting via a reaction between the acyl chloride and the amide groups or hydrogen oxide groups. Summarize the shortcoming of the above mentioned method. Due to the limited time, I won't repeat these words. Here are the three types of the work that we recently report. In our group, the amphiphilic copolymer is the main powerful material and tools. Compared with traditional phase separation method, there's no compatibility and leakage of the attitude. Related issues happen in the amphiphilic copolymer-based membrane. In this work, PVC-based copolymer PVD was used. The membrane is prepared via 2 steps. The first one, precursor membrane is prepared via NIPS process. Second one, the membrane is thermoannealed. Here we found the glass transition temperature for the copolymer is around 77 degree. Therefore, that is critical temperature to treat the membrane. In the following experiment, we found not only the temperature but also the annealing media and annealing time are the critical factor to arrange the polymer chain in the dense layer. The optimal conditions for the thermal annealing are as follows: happen at the annealing media, 80 degree at the annealing temperature, and 1 minute at annealing time. Here, the surface become dense, and the pore size is successfully reduced to the nano size. However, the surface charge does not change a lot, since no extra positive charge groups were formed. The positive charge of the membrane is mainly attributed to the tertiary amide groups. Due to the larger pore size and the thick separation layer, the membrane shows relatively low flux and low magnesium chloride reaction. However, the membrane shows a high reaction towards the positive dye with a molecular weight around 700, which is mainly ascribed to the electrical static repulsion between the surface and the positive dye. Due to the weak charge on the previous work, we introduced XDC, which can quaternize and cross-link tertiary MI group during the thermal process into the post-treatment. Obviously, the pore size decrease from the UF range to NF range. More important, the membrane become more portive. No IEP is found in the test range. Now, benefiting from the enhanced hydrophilicity and any enhanced charge, the membrane shows improved water permeance and magnesium chloride reaction. Of course, the membrane stability is very good. To solve the leakage of the additive during the formation blend membrane, the cross-linker PTGE was introduced to the casting solution after simultaneous cross-linking and quaternization using XDC. The PMIA blend membrane shows obvious positive charge. The pore size is reduced to 1 nanometer, and the molecular weight cutoff around 1,000. Interestingly, we found the membrane shows a relatively high sodium ion and magnesium ion selectivity, which is promising for water softening. This is a very recent work, which is published in the Chemical Engineering Journal. For the preparation NF membrane by interfacial polymerization process, the organic solvent is always needed. For this reason, we designed the novel membrane fabrication method derived from the polymer synthesis process. In this slide, we show the novel preparation procedure for positive charged NF membranes by nanoparticle deposition. Here are 2 steps. 2 steps are needed. One step soap-free emulsion. Step 2, coating and annealing. Here the milk-like emulsion. Here is the milk-like emulsion. The molecules were formed during the reaction, which the size around 16 nanometers. In our emulsion, no organic solvent is needed. After obtaining the emulsion, we direct coat the emulsion onto the polar substrate. When it was dried, the dense separation layer is formed. The composition of the synthesis copolymer and the nanoparticles was then regulated. Finally, the 1.25 DMCPS was chosen as the representative membrane for the further characterization. According to SEM images, the packing of the micelles was observed on the surface, and the surface was positive charged. The net zeta potential was above 50 microvoltage during the test range. According to the solvent transportation method, the pore size determined and 0.9 nanometer, with the molecular weight cutoff is now about 900 Dalton. The filtration experiment showed the salt reaction consequence is as follows. In order to investigate the practical potential of this NF membrane in separating oligopeptide and amino acid, 2 oligopeptides and 2 amino acids were selected as the model solvent source. Among them, GHL and GGL have the similar molecular weight and different charge properties, while the lysine and glutamine have the same molecular weight and different charge property. The rejection of the GGL gradually increases when the pH decreases, which is because GGL becomes positively charged in the acid environment, resulting in the stronger donor exclusion and leading to the high rejection rate. On the contrast, GHL maintained a relatively stable reaction over 90% in the neutral and acid due to stable and strong positive charge in these cases, resulting in the intensive donor exclusion. However, the reaction of GHL has a sharp decrease when pH in the alkene environment, since GHL becomes negatively charged and attracted to the positive membrane surface, resulting in an easy transport through the membrane. Hence, the selectivity is maximized under neutral and weak acid conditions. The similar separation behavior is also observed in the separation of the lysine and the glutamine. I won't repeat this word. Finally, we also compare the separation performance for the oligopeptides for or amino acids in this work that is reported in the literatures. The results showed that our membrane have the competitive performance with some lab-made and conventional membranes. Due to the limited time, I will skip my work on the positively charged membrane based on the interfacial polymerization methods. Roughly, two types of the calcium nanofillers was introduced into the PA layer. If anyone want to know more about this work, please refer to my recent publications. Here are the conclusions of our work. First one, positive charged NF membrane were developed by the post-treatment nanoparticle deposition and interfacial polymerization with nanofillers. This is the first time to prepare NF membrane from the nanoparticles derived from the soap-free emulsion polymerization, which is a facial and green method. The prepared membrane showed great potentials in water softening and biomolecular separation. More detailed evaluation and wide application scope will be developed in the following work. Now we thank the Professor Zhu at Zhejiang University and also thank the funding from China. Thanks for your attention. If any question, please contact me by email.